So the OCC on-chip clock, uh, OCC, the concept of on-chip clock, uh, we are going to discuss from Synopsys vendor. This particular document that you see is from the Synopsys vendor. Okay, we have I have the parallel document of OCC from Mentor Graphics also. Tessent means Tessent is a product from Mentor Graphics, and Mentor Graphics is owned by Simons. Okay, SIEMENS, Simons. So pretty much, if people might be aware of Simons company, Simons has acquired this Mentor Graphics. So since then, all the Mentor Graphic products belong to Simons. Okay, we'll have a differentiation. I'll just show you what could be the difference, but pretty much the concept of OCC would be same, and the structure also somewhere apart from the naming convention, pretty much it would be similar. Okay. Now, so on-chip clocking support OCC is common to all scan ATPG, basic scan and fast sequential and compressed scan environments. So basic scan and fast sequential and compressed scan are three different environments in theoretically, but practically will perform fast scan or a full scan with compressed. Okay. So this implementation is intended for designs that require ATPG in the presence of phased lock loop and clock controller circuitry. That means if you want to generate patterns, okay, if you want to generate patterns, ATPG means automatic test pattern generation. ATPG, it's a automatic test pattern generation. It got its name of ATPG because we use the tool, okay, and we are inserting scan insertion logic, and we are telling the tool to generate patterns. Okay, so it indirectly is an automatic test pattern generation which tool is performing. Okay, based on the algorithm. Now, at the same time, when we are using at speed testing, I mean, at speed testing is where you want the capture pulse, the at speed clock pulse. Okay, yesterday we discussed that the clock pulse in the capture stage. In order to have it, you need a PLL and a clock controller circuitry. So when you are using ATPG with PLL and clock control circuitry, then only you need OCC. Okay. So now what happened is we included all this PLL clock control circuit, everything into one component called OCC. Now OCC will include this PLL, clock shapers, dividers, multipliers, all of this. Okay, sometimes we have dividers and multipliers separately, but mostly if you're buying or if you're using OCC from Synopsys, all these are included. Okay. Now, in the scan ATPG environment, scan chain load unload is controlled through an automatic test equipment clock. So ATE clock. ATE clock is the clock that you give as a reference clock. So ATE clock means the tester. ATE means the final tester where we test the our design on a wafer. Okay. So when you are testing on a wafer, and particularly in the ATE, using ATE automatic test equipment, it has to follow the same sequence of shift in, capture, shift out for testing the design using the test pattern. Now there is also a sequence called load unload. Okay, before shifting, there is a concept called load unload. After capture, again there is a concept called load unload, and then shift out. So load unload, shift in, capture, load unload, shift out. So why this load unload came is particularly to what we call to initialize uh, all the control signals, logic, any additional pipeline stages or logic. There will be all these concepts that you will learn going forward when you learn compression technique. Okay. So remember that a load unload is something there you are trying to make sure that all the scan enable is in a right value. If you are doing shifting, then scan enable should become 1. So and all the control signals or registers um, before shifting in, are they in a correct value? Are they loaded with the correct value? So we will try to load all the control signals, additional registers or additional logic outside the scan chain. We do all of this, okay, during load and unload. So this particular load unload is handled by ATE clock, but this internal clock signals that reach each state elements during capture are PLL related. Okay, so there internal clock signals means the internal clocks that are going to each partition. Okay, uh, will be provided from PLL during capture, and load unload is happening with the ATE clock, that is a reference clock. Now OCC is helpful in handling this kind of uh, what we call differential clocking environments. So it will use the existing reference clock as input, and it will provide you the desired capture clock also at the same time. So OCC will handle both the shift or reference clock as well as the capture clock in one go. Okay. So for all the test conditions, this OCC can be utilized. So OCC clock will try to provide the capture clock at the required time, and when it is off, you will be able to give in the shift clock. So in the same clock path of yesterday that we have drawn and discussed, right? In the same line, you will have this OCC added. This is a additional circuitry added in the uh, clock path. Okay. So OCC is inserted in the form of a clock controller. So OCC clock controller. OCC flows can use either the user-defined clock controller and clock chains or the DFT inserted OCC clock controller. That means if you want to customize, like product-based companies, they customize their own clock controller and they use it. If you do, and still the tools are supporting that. If you don't want a predefined soft IP, the OCC purchased from the same Synopsys vendor or a mentor vendor, you can also use a customized clock controller and clock chains. So if you use an existing user-defined clock controller, you have to set user-defined commands to identify the existing clock controller outputs. So that's little risky. Okay. So what is that risk and what are the concepts and limitations? Everything we'll learn going forward. Okay. So as I said, OCC is required and used for at speed testing, because during at speed only we need that at speed clock, that clock pulse during capture. Okay, so remaining all this theory you can learn. I'll directly go to the image and I'll try to explain. So these are all the different clock type definitions. That means in reality, if you're working on OCC or any other type of clock structures, you will come across all these namings, different namings and uses of clocks. So reference clock, PLL clock, ATE clock, internal clock, external clock. So what are these? Okay, there are different type of namings and usage. So what is this? So reference clock means the frequency reference to the phase look loop. So phase lock loop, PLL. Yesterday in our session, I have explained you the reference clock coming externally to the PLL. That is reference clock. It must be maintained as a constantly pulsing and free running oscillator. Okay, so free running oscillator is something, a pure oscillator, the external oscillator, which will be free running. There is no control on that. So that means it will have a pure crystal oscillator. So it will continuously pulse. Okay, PLL, the output of the PLL, the PLL clock, the output of the PLL, it is also a free running source that runs at constant frequency that might or might not be same as the reference clock. Because reference clock might be some 100 megahertz, PLL clock will be depending on our user defined. If you want a 2.4 gigahertz or 4.8 gigahertz, you will get it. So the output of PLL is called PLL clock. So ATE clock. So ATE clock is a tester clock. When you try to uh, take a wafer, on the wafer you are trying to on a wafer, and on the wafer you have multiple dies. Okay, so let me redraw that. Not like this. Let me. Now each of this is a die. Okay, each one, every slice that you see. Why is it? Okay, middle one is gone. Okay, so these are all dies. I hope you remember this concept from where I have explained the wafer and die. Okay, this is a silicon wafer this is die. Okay, so there are many dies. Okay, so what was I explaining? Sorry. Uh, yeah, it's die. So your whatever the design you finally decide, I mean you are designing some SOC, right? That particular SOC will sit or will be integrated or built up on the fabricated on this particular die as a base. So this die will become your PCB or the base in which on which the SOC will be designed or that particular IC will be designed. Okay, this part is understood by everyone. This
Yes,
is
sir.
clear. Okay, sorry. Should I explain some again?
No, sir. Clear, sir.
Okay. Now, as we are explaining wafer, I want to explain one more concept here itself. Uh, so, on a wafer, as you can see, the extra parts, because these are equally divided into, so your IC will be, see, your IC will be either in a square shape or a rectangle shape, correct? Perfect square shape or a rectangle shape, correct? These are the only shapes that you expect, right?
Yes, sir.
Now, when you I mean, when you cross-sect this particular round wafer, silicon wafer, you will be losing all this additionally half, I mean, half curved ICs, I mean, dice, which are unuseful or not useful. Okay, so these are all wasted, and the rest, whatever you have, a perfect shaped cubes of the dice, they become the dice, perfect dice. And on that also, this wafer will be tested or uh, what we call it undergoes multiple wafer processing, which will mainly address the PVT concept, process variance and temperature. Okay, PVT. So PVT normally we call PVT corners. There are different PVT corners, but this meaning means PVT. Okay, corners are additional term that I will explain later. Now, process variance temperature they will be tested, and not necessarily all these dies perform on the expected die parameters. So, in order to become or select this particular cube into a perfect die, there will be a fixed parameters. It has to be eligible. That die has to behave according to the parameters. If it is not behaving, that becomes a bad die. So there is a concept of good die and bad die that we discussed when we are discussing on the wafers and fabrication process, right? So that good dies and bad dies are mainly decided based on the process variance and temperatures. So when you give this wafer to the ATE machine, ATE machine is nothing but ATE is nothing but a tester. Okay. So this ATE tester, when you try to give your design, okay, plus patterns, test patterns. Okay, when you give this this particular thing, okay, and this particular wafer to the tester will apply first the configure the tester. First, there will be a configuration of the design for the tester, because tester is a combination of a monitor, okay, a monitor, keyboard. It's like a computer attached to the ATE, through which we will be configuring the tester according to that particular SOC design or the project, and you will load in the wafer and you configure it with design and test patterns finally, and you test it on this particular die, assuming this particular die is your PCB, and you try to integrate that particular entire design, SOC design on that, imprint on that, and you test it. So this is the process of testing. So during testing, okay, tester has limitations. What are the limitations of a tester? Less uh, memory, low frequency input. Okay. Okay. Less memory, low frequency, and mm, you cannot change the design. Obviously, once design is fixed and configured, you cannot change the design. What you can change is the patterns. Only patterns can be modified. That is how you debug. That is how your DFT engineer is useful even in during testing phase. During design phase, you have done all kinds of testing, virtual testing, simulations, and all of that, and you finally said that okay, my test patterns are giving 99% of stacked coverage. Okay, stacked coverage, and 95% of head speed coverage. That is how you delivered it, and you came up to tester stage. Okay. Now, if you find that this coverage that you're getting at your end before getting on the silicon, on the physical level, at virtual level, at a design level, you got these numbers, but it has to practically be applied, right? Even after at silicon, this number should be uh, visible, but majority of the times it doesn't happen because of various reasons, because this is a actual silicon level. On silicon level, there are many factors, because this is pure chemical, and actual design, actual what we call silicon or physical testing. Okay, so actual behavior of transistor will you will be able to see only on the physical silicon die. So these are the main limitations that anybody can address. First thing is less memory and low frequency. So less memory is something, this particular ATE tester by default comes with limited memory to store the patterns and design. Particularly forget about the design, but test patterns has a limited memory. Okay. it cannot exceed that memory. So you have limited memory. That means your what we call the pattern size should not cross a certain memory size. So your test pattern should be less number of volume. Okay, the pattern size should be less. So that contributes to the less memory. Otherwise, it is very tough. Now low frequency. Low frequency is again it's a low what we call it's a slow clock. Okay, so what you can give it to the tester is I mean the availability of the clock within the tester is a slow clock, because when you give a high frequency clock, your tester design default tester design should be having high capacitive and resistivity to withhold that high frequency clock. So that is not possible by design. And if you try to, even if you try to give, okay, high frequency clock, that means high frequency clock is again high voltage, okay, or high fluctuation of current and voltage within the what we call um, design data toggling. And when you try to fully on the SOC design on the die with at high frequency, the die gets burned. Okay, so in order to sustain all of these during test phase, because see, in general, while the usage, the die after die has been tested and it becomes a proper IC, physical IC, and gets into market, you are using it as normally. Okay, and if you're continuously switching, I mean using the same button in your phone, like a power button or a up music up bottom and up buttons, or any touch button continuously, okay, what happens? Your circuit gets heated up because of the continuous toggling, continuous voltage fluctuations. Okay, because whatever you give, the user gives as input, internally the circuit has to behave, and continuous fluctuation will make the more what we call more usage of voltage, and more usage of voltage will cause more heat consumption. Okay, power consumption, obviously it is directly proportional to your heat. So when your power consumption increases, that means more heat is produced. When you more heat is produced, your that particular uh, product gets damaged, burned out. Okay. So similarly, during tester time, particularly in tester time, you are giving a random test pattern of 64-bit data. Okay, and that pattern is continuously 1001 or randomly, ultimately it is again a 01100. So this particular pattern is a continuous toggling of data. That means flip-flop has to continuously toggle during shifting. Okay, so if you have 500 flops in a chain, you have to shift in 500 times. You have to shift out 500 times. So in the test process, you're continuously toggling these flip-flops, and there is a continuous capture of at head speed. So all this will create more power consumption and will lead to uh, failure of tester, as well as the die gets burned out. And tester is approximately a single tester will cost 100 crores INR. Okay, one single tester costs 100 crores INR. I have given you the lowest price. Okay, the highest price is more than 780 crores. Okay, so it is too costly. They cannot afford that. Okay, the cost of tester is equal to what we call uh, a large product. Okay, even sometimes some client came with a concept that I need a design and my maximum budget is 10 crores. Even then, he has to get his IC tested on a 100 crores fab. Okay, so uh, the tester and fab is too costly for the manufacturers. So it has its own limitations. These are the main limitations: less memory and slow clock or a low frequency test clock available. So that means if you are testing any kind of design, okay, on ATE slot, okay, in that particular tester, okay, in that particular when you select this die, ATE has to provide the physical attributes of this particular all pins. So this has 40 pins, and 40 pins, whatever the GPIO pin behavior, clock behavior, oscillator behavior, everything that behavior the ATE has to provide. Okay, so ATE has to provide all the pin behavior from externally for testing purpose. Okay, now when you do that, the ATE has a limitation of slow clock. That means it gives only that 20 megahertz to 100 megahertz clock frequency only. That is equal to your shift clock, but it cannot produce your capture clock. So the same limitation concept is where we are going with the multiple PLLs inside, and the concept of OCC also comes into picture. So we are going to discuss that. Okay. So sorry if I'm being transitioning fast. So this concept is understood till this part. Is it clear? It might be too much, but the concept, if you understand it, I can listen again in recording if you want. But the concept is clear, right?
Yes, sir.
Any doubts? Can I move forward?
Okay, sir.
Everyone? Okay. So I have explained this concept because we are talking about ATE clock. So any concept, my responsibility is to clearly explain you the background of it and the behavior in real time. Okay, this might be useful, or you might digest this concept on a later on when you fully merge into this course content. Okay, so now it might be too heavy, but this will come in handy. So that is one reason I'm asking everyone to maintain notes so that you can revise to this concept again. Okay, and everyone is maintaining your notes.
Yes, sir.
Yes, sir.
Okay, please do maintain. That will help you, and it will be a very good handy during interviews. Okay, now ATE clock shifts the scan chain typically more slowly than a reference clock. Okay, this reference clock, this reference clock is a clock. This is the clock, right? Reference clock from external oscillator. But you are testing on a ATE. So when ATE you're testing, you get even less than a reference clock. That means, for example, your reference clock in actual TCB board actual behavior, you might get 100 megahertz. Okay. Again, I wanted to clear this both. Okay, both of that. Let me clarify. I'm about to give you the clarity between reference clock and AT clock again. If somebody has a misunderstanding, okay, just let me take any PCB board. Mm, let me take the Raspberry Pi. So this is your physical PCB board or a motherboard, what we call. Okay, these are physical layout and which we have multiple components. Okay, this is a physical layout. I mean physical environment, physical IC that you're seeing, and you have the individual ICs. Okay, multiple ICs, analog components, and you have capacitors, resistors here, transistors, filters. Okay, you have pins, GPIO pins. These are the GPIO pins, and these are also the GPIO pins, which has physical attributes like these are HDMI ports, chargers, USB, 3.5 mm jack, LAN. Okay, all these features you have, and a display board connectivity. So on a single PCB board, you have all of this, right? So when I say reference clock, you are getting it from a external oscillator. That external oscillator setup is done on a PCB board, somewhere where close to the real-time clock setup, and that is going into CPU properly. There will be a power management circuit. Okay, there will be power management circuit also on the PCB board. Now that reference clock is coming from a external oscillator, that is a physical oscillator, that analog component and circuitry that you will have. Okay, and your this is a PCB board. Do not confuse. This PCB board is not tested on the die. This single IC, this is the what you are testing on the die. Okay, all of your understanding. These ICs are tested on the die, are imprinted on the die, not PCB.
Yes, sir.
Is it clear?
Yes, sir.
Okay. These individual IC components are the one that get physically designed on these dies, not the PCB. Because PCB, if you take the size of wafer, will not be sufficient. If you take a big motherboard, okay, and you don't need that. These are individual separate components. Why do you need a tester or fabrication unit to design all of this? No, this PCB is manufactured separately, and these linings are done separately. Okay, but this connectivity, everything is again the representation of a block diagram. Okay, so the same block diagram. Whatever you see this block diagram, based on this block diagram only you are designing your design. But this IC gets manufactured separately. These components comes in separately. You try to the latest soldering. I mean, the machine will try to solder connect all these components. Correct? You're understanding, right? The connectivity soldering of all these components are physically done by the machines externally. Once all the components are in place. Okay, this is one SOC design with all of this. This is your IC. This is separate ICs. This is separate ICs. This is separate ICs. All of these are separate. Like this. Again, when you physically make, all these are formed here, and the connections that you see, the layer, the lines, are the lines same that you see as per your design connectivity. Okay, makes sense? Everybody, the concept is clear.
Clear, sir.
Yes, sir.
Understood, right? Okay. Now, reference clock is a clock coming from a free running oscillator. This is an analog circuit. Okay. ATE clock is something that you need to generate new, that is a separate clock provided by the tester. Okay. This is provided by the tester. That ATE clock only for testing purpose. So that might be what he's saying is that ATE clock might be less than the reference clock. Let's say 25 megahertz or 40 megahertz, less than the 100 megahertz of reference clock. Is it clear?
Yes, sir.
Yes.
Okay. The same purpose. Okay. Okay. And OCC, the necessity of OCC again is interlinked to the ATE clock. That is what you will learn here in this paragraph. See, this signal, ATE clock signal, must pre-exist, or you must manually add this signal when inserting the OCC. So when you are trying to do OCC, whatever the clock that you say, that will be connected to, I mean, you create a port called ATE clock. The period for this clock is determined by the test default period. Okay. Usually the ATE clock is not used as a reference clock, but it must be treated as a free running oscillator so that it does not capture predictable data while the OCC controller generates at speed clock pulses. That means if you do not have a free running oscillator means that it's a free running clock. That means there is no additional controllability on that. It should continuously generate the clock pulse. A clock pulse should always come with the expected period and the shape of the clock pulse. The X-ray proportion of the phase of high and low phase of this clock should always be same and continuously pulsing. That is a free running clock. There should not be any controlling element on the free running clock. That is called free running clock. If you have any controllability on that, I mean, if you have controllability in the sense you are trying to manipulate it and you want to on it, off it, on it, off it, and you have a switch to handle this, that's a problem. Or you are generating it again from a different source, which is not synchronized, or not what we call not stable. Okay, then it is not a free running clock. So your AT clock should be, the behavior should be like a free running oscillator. If it is not a free running oscillator, it might create ripples. When you say ripples are in analog, you say ripple is something close equal to noise. In analog communication, when you are talking on mobile phone or when you are listening to radio, the noise is a additional frequency or the pulse that got added, okay, along with your data that got captured between the transmitter and the receiver. Similar to digital, in digital, this is a additional ripple. Ripple is a small, slight, small portion of the clock. I mean, additional. That is a unnecessary clock. It is neither full-fledged clock, okay, or a zero value. It will behave sometimes. It's a spike, like what you see in a heart monitoring device. You see spikes, right, in between. That kind of spike in digital square pulse, if you see, that is a ripple. Ripple might be caused because of unstable clock. So when you get that ripple accidentally, what happens, even a ripple can excite the flip-flop, and flip-flop might take this particular ripple as a clock, okay, and it might latch the data. That means it might toggle the data. That is very bad for our design. Okay. So if the free running oscillator is not available, it will be very bad for us. Okay. During at speed testing, okay, that one clock pulse that needs to be generated during at speed capturing, if the AT clock is not stable, it will create ripples, okay, that will create unnecessary capturing of data. Okay, till this part everybody understood?
Yes, sir.
Okay, the ATE clock is called a dual clock signal when the same port drives both ATE clock and the reference clock. So we'll go and see the structure again of OCC. So you'll see ATE clock behavior is a called it's a dual clock signal which will behave as a ATE clock, okay, and it will also sometimes drive the reference clock during testing phase, okay, because you are replacing the reference clock coming from external oscillator in the tester phase with the ATE clock. So ultimately, ATE clock is feeding to the reference clock in tester. Correct? On a die, you cannot get this physical oscillator, right? You're understanding, guys?
Yes, sir.
So, in order to avoid that, I mean, in order to replace this particular oscillator clock, we are providing AT clock. So, AT clock will go as a reference clock in the design for testing phase. Okay, that's why the behavior you can, it's also called as a dual clock signal. Okay, the same port that drives reference clock also drives AT clock during testing phase. Okay, now there is also technology called internal clock. What is internal clock? So the OCC controller is responsible for gating and selecting between the PLL and AT clocks. Okay, we'll see that in the schematic of OCC. Then we will discuss that in depth. So let me just yeah. So it's a simple representation that you see. Okay, a reference clock, the ATE clock, external clock, and the internal clock. So internal clock is what you see is a OCC controlled output that is going into the design to the flip-flops. That is internal clock. Okay. External clock can be a reference clock or ATE clock, any external input. A primary clock input of a design that directly clocks flip-flops through the combination logic without the use of a PLL clock. Okay. So this particular clock, external clock, there is no PLL in between. This is directly going to flip-flops. Okay, from a primary input of the SOC. Considering when you see this kind of structure, this is a primary input. That means it is directly available to the IC pin. Okay. So now let's talk about the real implementation of this reference clock connected to PLL. So as I said, reference clock is 50 megahertz. We have taken a random number from 25 to 100 in between 50 megahertz, which is going to PLL. And PLL clock, we are bringing out as an assumption of 300 megahertz that is going and feeding to OCC controller. Okay, we will also see the internal diagram of OCC controller. So this is going to OCC controller, and OCC controller gives out the output of 300 MHz for capturing, and the same 10 MHz or 80 clock that you use for shifting. Okay, as I said, this reference clock should go for a shifting purpose. Okay, but for testing purpose, we have created one more port. Okay, that port we are trying to give for shifting during testing phase. But once testing is done, everything is done. Okay, we also connect this reference clock to this particular design once this testing is finished, so that next time once IC is done and ready available, this reference clock will be going for shifting purpose post manufacturing. I mean, in the process of manufacturing, the connection will be established, and post manufacturing, you will use this particular clock as input. Okay, because these two ports will be same in real time. For your understanding, now it is shown separately. Okay, when this is implemented in a physical IC, like I mean the physical PCB connectivity, the same port, it is the same port. You will get the reference clock, and the same port is connected to ATE clock in ATE tester, which will give only 10 MHz. Okay, so this is internal image. When you see, you will understand. For now, for your understanding, it has separately shown, but in real time, the image, this reference clock will also behave as a shift clock. I can show that, and this is a bigger image. I'll open easier. Hmm. Hmm. This is also good. As I said, there will be different OCCs available in the market in the name of soft IP. People will purchase, and few are what you see in the manuals are originally provided by the EDA vendors. So EDA vendor circuits will be little bit complicated to understand because of too much clumsiness. I mean, being for you when you are new, it will be difficult. But first time before going into the complicated circuit, I want to show you a simple circuit, something like this. First, we'll try to understand mechanism. Later, after seeing this and understanding this, we'll come back to the original uh, synopsis OCC or mentor OCC. Okay. Okay. Let's understand from this particular image. Scan clock is nothing but your reference clock. Actually, the same scan clock will go as a input to the PLL. Now, scan clock is separately shown. Okay, and PLL clock is going into a clock gating cell. So we have to learn what is a clock gater also in this process of learning OCC. We will learn it. Okay, for now, let's try to digest this concept where your scan clock or the reference clock is going to PLL, and that is also a separate path, free path. Reference clock directly going as input to this particular mux. Okay, so this mux select line is again a scan enable signal. When scan enable is equal to set 1, this particular scan clock, which is a low frequency clock, will go as a shift clock for shifting. You know the behavior of scan enable, right? So when scan enable is equal to 1, it's a shift mode. When scan enable is equal to 0, it's a capture mode. So when scan enable is 1, what happens? 1, your scan clock or the reference clock will go as a input, and this mux out will be directly going into the particular flip flops. Next, when scan enable is high, is 0, you are getting this PLL clock gating output out of this particular mux and feeding into the design flip flops, and we use that only for a capture phase. So this particular activation of OCC, we will program it in our pattern generation environment in such a way that this one or two or whatever the number of pulses you want, that you want at speed clock or that particular high frequency clock that you need, okay, that clock pulses you will generate, okay, only when required and only that capture stage. So you will program it accordingly. So we will learn that programming of the OCC during ATPG stage, okay, not now. Now let's see the remaining features of this. To this clock gating, there is a input coming from PLL, okay, and there is input coming from this particular shift registers. There is a OR gate, this particular OR gate, okay, output you are going to get it to this clock gating cell, okay. This particular structure that you see is a programming of this shift register to produce the number of pulses that you need, okay. So first thing is the first particular flop is a synchronizer to synchronize this scan enable value or stabilize this scan enable value. So the same scan clock will go to this particular flop and scan enable will feed into this, okay. And once in one clock pulse, the scan enable will be properly settled, and going forward you will program scan enable in such a way that you will fill this particular 5 registers in such a way you produce the output, you take the output from Q3 and Q5, that particular clock pulse, okay, that particular 1 or 0. So when you program that, the clock gating cell will give out that 1 or 0 value. 1 means high, 0 means low. So you will get a proper clock pulse using this particular behavior, and the number of pulses you want, that you will program through scan enable. So this particular structure is also helpful in producing a clock output without any glitches or spikes. So previously I have told you ripples, right? So the ripple is a analog explanation, okay, but in digital you call it as a glitch or a spike, okay. So these glitches or spikes you will not be able to see if you have a clock gating cell connected. So we'll learn about clock gating cell going forward. For now, this is the behavior and how you get a clock pulse, that one clock pulse for capturing phase, okay. So this particular OCC, why you need is, in tester you are trying to physically establish a on-chip clock controller circuitry. So even if you do not have a available oscillator, okay, and you are getting ATE clock and you want to generate you want to generate a desired clock, and with that desired pulse, during our DFT execution for the testing purpose, you definitely need a separate clock controller mechanism, that is that on-chip clock controller. So on-chip clock controller will produce the perfect capture pulse required to test the design at speed frequency. Okay, this is a statement. You can write it as your wish, or you can modify it accordingly, but that is the requirement. Okay, so this is understood. This behavior is understood. We'll go and learn about clock gating cell going forward. So this is understood, right? This is the actual OCC, simple way of representing OCC. So everyone,
Yes, sir.
okay. Now let's see the same circuit you will see in the test end. This is a test end OCC. Let's see. This is little bit brief and detailed, but here I don't see the clock gating cell. Their clock gating cell is not there. This is a different type of OCC without clock gating cell. This is without clock gating cell. Okay. So this is the representation. You can see test enable or a scan enable. When they are scan enable or test enable is high, that means it's a shift mode. You're getting a slow clock. And when test enable or a scan enable is low, this is capture phase. You need the fast clock pulse. And to generate this fast clock pulse, we are using OCC. Okay. So as in the previous image that you have seen, scan enable, there is a single flip-flop that is trying to synchronize the scan enable. Here you have how many? 3 set of synchronizer flops or a synchronizer cells, okay, that are trying to stabilize this test enable value, followed by a PLL cycle counter. Okay, and there are multiple AND gates that are taking in the input from these shift registers, which will help produce the clock as required. So these are called clock control shift registers. So what you see here, these 5 registers are properly shown here. Okay, the number of registers depends on the number of clock pulses you need. Okay, so your capacity. So you have, so while inserting OCC itself, you have to decide how many clock pulses, the maximum clock pulses you would be requiring. Once your controller is inserted, you cannot change it. So during insertion itself, you have to finalize. So this architecture, the DFT architecture, our architect will decide and finalize the configuration. Okay, for PLL, we might need the maximum 5 clock pulses or 6 clock pulses. Then you you give that input to during OCC insertion in the design, and tool will generate that many number of flops accordingly. I mean, if you are using a EDA provided OCC, or if you want to use a custom OCC, then you have to program and write that particular code to produce that many clock pulses. Okay. Next, let us go into the actual OCC. Clock gating cell. This is more of a behavioral explanation. I'm looking at clock gator. OCC controller. I don't see clock gating cell here. This is a okay. DFT inserted OCC controller datasheet. Okay. Let me just see if we have any other image. If not, we'll just go and explain in the test manual. Test is more clearer. So ICG is a clock gator. ICG means integrated clock gating cell. Mostly all the cells that you see nowadays is integrated. Integrated means it is a written part of RTL coding, not inserted during DFT insertion. These are already part of RTL coding. During RTL coding only, they have written OCC and with ICG connections. Let's say, let's discuss this. Okay. So, as I said before, OCC will have the initial components. I mean, it has written here in a specific way of selection of clocks. There is a marks, and this particular portion will go into a clock chopping control where you have that registers, right, to perfectly give out the clock pulses, followed by clock gating cell and all. So let's see more of a clear image. This also we have seen previously. Reference clock going into PLL and a slow clock going to the same mux. Okay, followed by this shift registers and clock gating cell. Let's see more clearly. Okay, not like this. Yep. So as I said, this will be too complex, complicated because of too many gates, additional gates. Try to see from a far view perception. That means try to see this image that it is nothing. Okay, it is so simple. Look at it in that way. Then only you will be able to digest this. But the concept is same. The circuitry is little more elaborated and detailed. Okay. Let's start from here. The inputs. Okay, what you see. So go along with me. It will be easy to understand. Okay. Start with the left side. Scan enable. Capture cycle width. So scan enable is a signal that you already know. I have explained. Capture cycle width is something. The capture cycle, that means that how many clock pulses you need, right? So this is a command for test and OCC. You can program this in such a way that 5 is to 0. That means six clock pulses. Okay, 1 is to 0. That means you can have 2 clock pulses. So based on that, tool automatically will configure the number of shift registers required during insertion. Okay, this capture cycle width is helpful. So remember that it is more convenient for you guys if somebody asks you to explain OCC in depth, or somebody in interview they're expecting OCC and this pins explanation. So remember this pins more clearly. Okay. There are some blunt people who knows only test and OCC. They don't know synopsis or cadence OCC. So they will expect this kind of environment and answers from you. So remember that. So I'm trying to explain this clearly for you. It is more commonly used OCC across the market in the semiconductor market. Now, this is the command or the pin that will configure number of clock pulses that you need. Scan in port. This is this OCC is inserted and in the path of clock path, right? So again, if you want this OCC also to be controllable, scan controllable, then there will be extra pin called scan in. That means every component or every logic in the SOC design should be controllable and configurable to be testable by the DFT logic. So when you're trying to additionally add OCC part of this DFT insertion, you are also making sure that OCC is also every logic gate. That means all these gates, everything is again controllable and observable. That means you can also stitch these particular cells, I mean these particular flops and these particular cells in such a fashion that you can also test that. Okay, but most probably this OCC will be excluded from the scan. Okay, you will not stitch this with the logical testing of scan flops, that scan chains. Okay, this scan in and scan out, this chain will be separate. Okay, we will not mix this particular chain with that what we call the traditional scan chains. Okay, this is separate and this will be tested as part of OCC during OCC testing, I mean the XP testing. Okay, so OCC gives the future to also make sure that OCC is also controllable and observable. That means you might end up having manufacturing defects on OCC if you don't test it. Okay, so for that, tool will also generate separate pattern to test scan in and I mean the logic in this particular OCC. For that, you have a scan in and a scan out properly. Next, fast capture mode. Okay, fast capture mode is a capture mode in which you will try to capture the pulse. So test mode, shift only mode. So shift only mode is a shift mode. Test mode is a scan mode or the global signal. It's a additional control signal on top of scan enable signal. Okay, test mode or a scan mode is an additional control signal on top of scan enable. So test mode is also called as DFT mode. Okay, test mode, scan mode, DFT mode, all are one, all are the same. Now there is a fast clock and a slow clock. The same slow clock and fast clock that you have seen. So fast clock is nothing but your high frequency clock. Okay. So within this diagram, the PLL is not there. This is pure OCC, on-chip clock controller. Okay. So PLL is outside. That you're getting fast clock from that PLL. This is purely OCC control logic. Okay. So what we are seeing is this one. PLL is outside. Okay. So each pin behavior is explained here and how you program it. And behavior when capture enable is high, what happens. Okay, all these are explained in each mode. Functional mode, the behavior of OCC. Shift mode, the behavior of OCC. Okay, and this is an overview of the block diagram that you see. You can enable or disable a certain OCC that is going to certain partition. So the benefit of OCC is also that you can enable that particular clock or disable that particular clock during tester phase. Okay. So that will, what happens is, by default you have, example, in here what you see is a three functional clocks, f clock 1, f clock 2, f clock 3, that is going to three different designs within that SOC. The different blocks might be, or at same block different portion of logic that is needing what we call high frequency, low frequency, or mid frequency. So irrespective of that, you don't want certain portion of logic to be active while you're testing another logic. That will save power. So power means when you are trying to do testing, your agenda is to make sure that power consumption is very less, or the total power consumption when you're trying to toggle, when you're trying to shift in, capture, shift out during these operations, your agenda is to also consume less power. In order to consume less power, when you have segregated and when you have different clocks and you have OCC for each clock, okay, each clock domain, you can control them, right? So when you don't need to test all the clock domains at a time. On when you want to test only one clock, okay, you can off the remaining clocks, so that will reduce the power consumption on the single stretch. At a time, if you are owning all the clock domains and all data connected to all these three clocks are on, that means your entire that particular block that you're testing or SOC that you're testing, all logic is on and huge power consumption. Even if you're testing at low frequency or high frequency, it's still huge power consumption that might end up burning the IC. So OCC will give you the benefit of low power consumption. So you can activate or deactivate that particular clock with the help of OCC. Okay. The concept is clear. We
Yes,
will
sir.
retouch the OCC again during ATPG before going to ATPG. Okay. Or during at speed testing and all. Okay. We'll learn this concept again. I mean, we'll touch this concept again. So by that time, you will get adapted to the circuit and all. Okay. So this might be look clumsy, but you don't need to by heart this particular entire circuit. You can just understand this particular simple circuit. Okay. I'll try to share this particular. I think I have this presentation of OCC from digital test architecture, or I think I have given you test books, right? Mm, did I give this test book, VLSI test principles and architectures? I think I have given, right? In this, you will have OCC. Even if you don't have in this, I will try to send you that particular presentation, which will have the explanation of clock controller. Okay, so need not worry on that. So try to understand this behavior, and this particular on-chip clock controller is explained in YouTube also in detail for your understanding how this clock pulses are chopped. Okay, so if you want to spend time in learning in depth, if you don't understand, then you can go with the YouTube understanding of on-chip clock control. This is in generic concept, okay, of OCC. So what additionally if might need is, if you don't understand this particular behavior, you can uh, learn from that. So now we are going to learn about clock gating cell. I'll try to explain here. Okay. So far it's okay. I'm going to explain clock gating cell now. Shall I go? Shall I proceed further?
Okay, sir.
Okay, sir.
This is AND gate. This is OR gate. Okay. This is your clock gating cell. So when you see this kind of structure anytime with a latch followed by AND gate, and one of the input of AND gate is coming from the clock that is going as a enable signal to the D latch. Okay, then this behavior is itself is a clock gating cell. Okay, so clock gating cell is a, the naming itself is a, it's a clock gator. It's a gator. That means you can on the clock, I mean you can allow the clock or you can off the clock. It's up to you. Okay, in order to enable a clock gate or circuit, you can just create an AND gate, right? You just create an AND gate, and you can control through AND gate also. You can directly control the clock enable or disable, right? So, but we need a ripple free or a glitch free clock output. So, in order to remove or eradicate any sort of glitches, okay, we are having a proper latch, okay, and this latch will take care of any ripples coming in this way till this way, okay. Once we get a clock to this part, you have no glitches. And if there is a possibility of glitch outside this clock gating cell, you can just have a clock synchronizer cell output of this particular clock gating cell. Okay, you just add a clock synchronizer. Sometimes what happens is, recently I have seen most of the designs, a clock synchronizer comes along with the clock gating cell within a same cell. Okay, so it's a clock gating cell with a synchronizer. Okay, so ultimately what you want is you want to gate the clock and you make sure that it's a glitch free. Okay, so what is the D input of this D latch? This D input of D latch comes from, you want to see, if you want to give 1, okay, 1, and let's say it's a 0, okay, what happens? You get 1 here, right? When you get 1 and your clock enable is high, okay, you get 1 here, and 1 1, what happens? You get a 1 value. That means what you are getting? You are getting a active clock pulse. Okay, now this particular clock pulse will stay this value until you program it to be, again you want 0, again program it to 1, 0, programming. So it depends on the clock enable signal and the D input. If your D input is always high and your clock enable is 0, okay, then what happens? This clock will not toggle during that particular level. So this is a D latch. It's a level sensitive. So level sensitive means when it is high, it is high. When it is low, it is low. It will not it's not like a flip flop to maintain one full clock pulse. Flip flop will maintain one complete clock pulse. For D latch, it will latch out with a half cycle of that particular. Half cycle duty cycle of flip flop is equal to the full cycle of a D latch. So it's just 0.5 nanoseconds. If you take this complete this complete if you take this 0.5 nanosecond, if you take it as a complete 1 nanosecond, okay, half of 1 nanosecond is your 0.5 nanoseconds. So your D latch behavior is level sensitive. That means it will be high when clock enable is high, and when clock enable is 0, again this will go 0. So this is perfect thing to help out in clock behavior. Okay, so D latch helps us in providing you the clock. If you want a clock, you will get a clock. If your D input is if this particular clock enable itself is 0, Okay, both again this particular one input of OR gate is your enable or a test enable. The other input is the functional enable that is coming from a functional logic. FE and SE or a test. So these are the two inputs. Functional enable means, remember that functional enable means, let's say this is your SOC, okay, or this is your partition. Here you have that particular port, clock port, okay. From this clock port, okay, I mean sorry, this port is your uh, enable signal, clock enable signal. Okay. This is your clock enable signal, direct top level port. Now, these are part of this clock enable port will come as part of your RTL design. When you have a clock, obviously you will have a clock enable. So this clock enable, okay, will have a lot of logic in between until it reaches the functional enable. Okay, from here to here, there will be lot of logic. Logic can be gates, latches, or anything, or muxes, or anything. Okay. So all that will this logic, when you say functional logic, it is the value output of functional logic might be X, okay, during testing phase, because during testing phase functional logic is disabled. Functional logic is disabled because functional logic might have flops, okay, for which the D input is unknown because we are not toggling D input. Okay, this is behavior of during scan or shifting. Okay, only the SI path will be active. SI means scan input path, active. So you will have a proper value on SI, scan input. Okay, so functional logic will always be unknown. So if there is a flop here or a mux here, the output is X. You don't know it. Okay, so this you will get controllability by in during DFT you define this particular clock enable signals. Okay, and you also define this scan enable test enable signals. So you program this particular clock gating cell correctly in such a way that you get a proper output from this clock gating cell during your testing. I mean, now there are two scenarios. Before jumping into two scenarios, till this concept you understood, right? This is understood.
Yes, sir.
Yes, sir.
Now, the presence of clock gating cell or the usage of clock gating cell will be like either in the OCC, you will see clock gating cell part of your OCC that you will not be able to do anything on that. Okay, OCC clock gating cell is OCC clock gating cell. You will not touch it. There will be functional clock gating cells and DFT inserted clock gating cells. So there will totally how many you have? functional clock gating cells in for all the functional clocks inserted during in the RTL itself, the RTL design by the front end team. Front end team means the RTL design engineer. Okay. Second thing, one more possibility of seeing clock gating cells is the OCC. OCC will have inbuilt CG. Now, the functional clock gating cells are also sometimes called IGCs. IGC, integrated clock gating cell. Okay. This is OCC clock gating cell. Next, one more is DFT inserted clock gating cells. So this OCC is also part of DFT, but OCC is a soft IP, so you don't separately mention it. So you try to insert clock gating cells when you try to create new clocks, or particularly when you try to do embedded insertion. Okay, you add clocks. Any new clock path that you create, you add clock gating cell in DFT. Okay, so tool will try to add clock gating cell. Either I mean, if it is not embedded, you have to manually add clock gating cell. If it is a BIST, automatically when you try to do embedded insertion or logic BIST insertion, tool will create clock gating cells in the clock paths of DFT on the DFT clocks. Okay, these are the three usages or observations that you will see the usage of this clock gating cell. Okay, so this three is understood. Did you understand this?
Yes, sir.
Next. Okay. What else? This concept. Okay, this is clear. What else need to be explained in OCC? I mean the clock gating cell. So this is the commands that you do. You will learn that later. The commands through which you try to insert clock gating cells for OCC. Okay, all this part of if you click this, it will not go to solnet, but this is the command, one of the commands. Along with this command, you will have other commands also that you will learn during labs. Okay, and we'll also learn the concept of don't touch, not scan during scan insertion flow. Okay, we'll discuss this later. We'll come across this particular attribute many times in the course duration. Okay, and we'll come across clock gating cells also multiple times. We'll see that. So this is a command where you define clock gating cell. Sorry, the OCC, the clock controller. Okay. This is for synopsis. For Tessent, the syntax and flow will be little different, but the same. I mean, similar to like this only. Okay. Not all OCCs will have the feasibility of providing separate ETE clock port. Okay. Remember that. Tessent will have a different behavior. Synopsis will have a different behavior. But the purpose and usage is same. Okay. Synopsys has more feasibility because Synopsys is so proud that it has its own synchronizer. So Synopsys synchronous, I mean synthesis tool. Synopsys has its own synthesis tool, which can properly synthesize any kind of OCC, even how much complexity it is. Okay. So it has advanced features also for like 1x, 2x, 4x clocks. You can have as many clocks as you want in a single clock controller. It can control that. Okay. Um, we'll come back to OCC later. So again, after scan insertion. So far, this is the behavior of OCC and internal structure of OCC. Okay. So far, so good.